Okay guys, so we're starting trigonometry. So trigonometry, definition of the word trigonometry means the study of triangles. Generally, it means the study of right triangles, or at least that's kind of where we're going to start. So trigonometry starts, this whole gigantic branch of math and human accomplishment starts by just looking at something really simple, which you've seen a little bit already, I'm sure, which is a right triangle. What's special about a right triangle? Has a 90-degree right angle, exactly. So I've got one up here. Supposedly this guy's a right triangle. My example, I don't have anything on there that says it's a right triangle. Which angle do you guys guess is the right angle?
The square one.
That one, yeah.
One that looks like a little square. How do you know for sure that something like that is in fact a right angle?
Those boxes.
So these, you're saying these have to be 45 degrees?
No.
They can add up.
They have to add up.
They have to add up to,
180.
so these two have to add up to
No, all
another
over.
90, so that the total will be 180. That's good, that's true. Very good.
Yeah.
How do you know for sure this is a right angle, though? This one might be like 80 degrees, and then those two could add up to 100 degrees. That's possible, and it happens a lot of the time. How do you know for sure that this thing is actually a right angle?
I just kind of looked at it and I was like, that's a right angle.
Yeah, but you can't do that, man. I know that's what you did, it's cool. Carson?
Box in the corner tells you it's the right angle.
Yeah, but I didn't have that box originally. You guys hypothesized that that box was there. How do you prove that this is a right angle triangle? You guys know. Jensen?
Because it has the two straight lines.
Yeah, but you don't know that they're straight.
Why did you say
I'm a terrible artist.
Oh.
Connor?
Pythagorean theorem.
Ah, so you should try the Pythagorean theorem and see if it works. So how's that go again?
A squared plus b squared equals c squared.
Okay, so for this triangle, we're going to go 7 squared plus 24 squared equals 25 squared. How do you know 7 was A, 24 was B, and 25 was C? Well, these two don't really matter. I mean, those are the legs of the triangle. How do you know this one is C? That does matter. You can't mix it up with A or B. Michaela? That's the hypotenuse. How'd you know that one's the hypotenuse?
Because it's the longest.
The hypotenuse is always the longest, correct, Jacob? The easiest way to identify the hypotenuse, guys, is the hypotenuse is always across from where you suspect the right angle is, even if they don't tell you, okay? It's across from the right angle. You gotta remember that. So that guy's the hypotenuse. Let's see if this actually works. You guys might need a calculator if you don't know your squares this high. We know this one's 49. 25 squared, do we know that one? That's one you should know. It's 625. 24 squared you might not know. I don't know, I always forget it. Is it 596 or something? I forget it too. You guys tell me what's 24 squared? 576. Dang it, I knew there was a 6. So let's see, what's 49 plus 576? You guys want to check that out?
Oh, it's 625.
That is proof that that's in fact a right angle and this is a right triangle, okay? So what I want you to understand in the big picture, this is the small picture, right? Thinking about the big picture here. Trigonometry is not just going to be about right angle triangles. That's just the beginning that spawns an immense amount of other things, okay? So we're going to be able to look at any kind of triangle we like, whether it's a right or not, and then this is going to spawn a whole other branch of our library of functions, 6 whole other new functions, which are like the most common functions that actually exist in nature. And then it just goes on and on and on and on and on. So trigonometry is a very prolific branch of mathematics. That makes sense. It's kind of in everything almost. So it starts out with just looking at triangles like this one, though, okay? So there are 6 ratios in all of trigonometry. You're going to learn all 6 of them today. 3 of those ratios are the sine, the cosine, and the tangent. They each have a partner ratio. So let's write that down in our notes. You want to take note that there are 6 trigonometric ratios. A ratio is a way to compare one thing to another, right? So they're fractions. And you need to have them memorized as quickly as possible, okay? That's the foundation of all trigonometry. You can't be wondering about them. So Jacob and a couple other people yesterday when they were looking at the pretest, said they kind of knew this thing called SOHCAHTOA, so SOHCAHTOA is a way to remember that. So let's write that down. You have to know how to spell it though. So I've never been a fan of SOHCAHTOA. See, because mnemonic devices to me always seem like extra to remember rather than just remember the real thing, but some people like it. So I'm gonna write it down. So SOHCAHTOA's, that old crazy Indian word, you gotta spell it right. So, ka, to. So how does SOHCAHTOA help you? Well, it helps you remember the basic three ratios. The first ratio, sine, is opposite over hypotenuse, the lengths of those two. Cosine compares the adjacent to the hypotenuse. And tangent compares the opposite to the adjacent. So can you guys see how that might be helpful in remembering? I personally have never used that, even when I was small. But you can use it if you find it helpful. Okay. There are also three other ratios, which are the reciprocals of these. So really, you really just kind of need to know three and know which one goes with which. So we're going to use that example triangle with these ratios in a second, but let me write down the other ones. So there's sine, cosine, and tangent, and then they're reciprocal partners. I'm not going to write them all the way out, but this is called cosecant. That goes with sine, that's its partner, and all cosecant is, now I'm not writing it out, I'm writing its abbreviation, right? The cosecant is just going to flip this. So instead of opposite over hypotenuse, it's going to be hypotenuse over opposite. Okay, so I'm just abbreviating now. The partner of cosine is going to be called secant, and it is hypotenuse over adjacent. Remember, these are just lengths of things. This is the length of the opposite leg, the adjacent leg, the opposite leg, if you really want to write it out all the way, which you guys aren't going to be. So. Okay, and tangent's partner is called cotangent. That's the easiest one to remember. And of course, it's adjacent over opposite. So really, if you just know the basic three to get those, you just flip. So it's kind of just three things to remember. Does that make sense? So they are all 6 functions. We'll be learning them and using them all in different circumstances. They produce 6 unique graphs that we'll see in a couple weeks, probably 2 weeks, I think it'll take. And we'll see 6 new graphs to add to our library of functions, which are extremely common graphs. Okay? So let's look at this example. So whenever you're thinking about a trigonometric ratio, you need to think about a specific angle. Now there's the right angle. You're never going to use a trig ratio really on that right angle. I shouldn't say never. Pretty much never. You're usually going to use one of the acute angles in the triangle, one of the other angles. They don't even have to be acute later on. So I need to pick one to focus on. So let's say that this guy has angle theta here. That's probably the most common angle name in trigonometry. So if I'm looking at theta, what's the sine of theta? What's the cosine of theta? What's the tangent of theta? Let's write it down. So sine of theta, that's how you write it, abbreviated. The cosine of theta, you don't read this cos circle thing. You read this cos of theta. Cosine of theta, excuse me. The tangent of theta. These should be all really easy things to do. So you've got your own triangle on your practice, guided practice there. You'll do your own in a second. Let's do mine first though. So if we're looking right here, sine is opposite over hypotenuse. Opposite over hypotenuse. So this is 7 over 25. Cosine of theta is adjacent over hypotenuse. Adjacent in Latin, the Greek root goes back to, it means next to. So what's next to theta? Well, these two are next to theta, but that one's hypotenuse. The adjacent must be the 24. So it's adjacent over hypotenuse. And you can see they're each ratios, right? I said they're ratios. And the tangent of theta is
Opposite over adjacent.
opposite adjacent. Okay, so if they ask you for the partner functions, I like to just line them up next to each other. If you do it that way, you'll start to remember which one goes with which. It won't be a big deal. They go with each other, not just in terms of ratios, but in terms of graphs and all kinds of other good stuff. So it's important to remember which one goes with which. So cosecant. See, now for cosecant, you can remember it the hard way and say, well, cosecant is hypotenuse over opposite. Or you can just be like, it's that dude's partner. So like,
25/7.
exactly. That's how I do it. This one's that dude's partner. This one's that dude's partner. Now, of course, you can remember cotangent is actually adjacent over opposite, but it starts to get easy to mix them up. I just remember the basic three and reciprocal them. And I think that's the easiest way to do these. Okay? So why don't you guys, and anyone watching the video, if you have the guided practice worksheet, go ahead and do the first example. You should be able to do that, no problem. Okay, so the second thing we want to know about trigonometry are the special right triangles. I think you guys have probably heard of these at least before too. There's two special right triangles, and you also need to memorize the side relationships in these special right triangles, okay? So this is one of the other things you need to memorize in trig. There are a decent amount of things to memorize in trig. You can really boil it down to maybe 5 little things, though, for all of trigonometry, if you really know them. So, okay? I am not good at memorizing stuff. I'm good at knowing things deeply, though, and that's how I just branch out from those things. Does that make sense? So, special right triangles are things that come up a very often. It's terrible, terrible English. So, what special right triangles are these? There's one that looks really symmetrical. In fact, it's an isosceles triangle. It's not quite equilateral, because if you've applied Pythagoras to this, you'd find it wouldn't work if it was equilateral, so good idea though, Jacob. What angles are in here if these are the same, these sides are the same, and it's an isosceles right triangle? 45. So this is what you guys were talking about earlier. So that right triangle is called the 45, 45, 90 triangle. So that's a very common triangle, so you want to have it completely memorized, okay? So I'm going to tell you the side lengths in a second. They don't come from somewhere mysterious. The other one is a little bit different, also extremely common. It has a smaller angle here, which is 30 degrees. It's a right triangle. That's 30 and that's 90. What's the other one? 60. So that's the only way it's going to add up to 180 total, right? So this one's the 30, 60, 90 triangle. Now sometimes you look at the 30, sometimes you look at the 60, it depends. So if the angles are the same on this first one, then these sides have to be the same. That's what makes it isosceles. That's a theorem in geometry, in fact. But, so if we call this side length S, then this side length has to be S units long as well. And you could use Pythagoras. I'm just going to give you the answer. But if you use Pythagoras to solve for the third side, then you'd get the square root of 2s. Okay? In the 30, 60, 90, you also start with a basic side of s. You call the smallest side, the opposite the 30. You call that a side length. And then, using Pythagoras, you can figure out that like this side is the square root of 3s, and this side is 2s. So this gives you a way to look at any dilated size or shrunken size of these triangles for any size of s. Does that make sense? In this class though, and most of the time in trigonometry, you're always going to want to put the most basic possible length in for s. So what would be the most simple side length for s to put in possible? What size is the most simple measurement possible? Little kids start learning to count by 1. So we're going to put side lengths of 1 to begin with. And pretty much this is the triangle you really need to remember. So if I put 1 here, it's really just going to be square root of 2 times 1, which is 2. Square root of 2. So that's the thing you really need to memorize. Now, If you by chance see a 45, 45, 90 triangle that's bigger, you can just stretch it out by multiplying all these by the same number. Does that make sense? That S size. So this guy, we're going to put a 1 in for there, a 1 in for there, and a 1 in for there. So that's the two triangles that I would definitely memorize. You won't even have to spend any effort memorizing them if when doing your assignment you try to do it without looking at your notes. But when you have to, you look. So let me explain one place where this might be necessary to know these side lengths. If you have a triangle like this guy and it says solve for x, and you need to find that side, it's a right triangle, right? Why don't we just use Pythagoras to find how long x is? We don't have, you're saying that we don't have b, this guy's b, and we also don't have a. So we're missing two things. That means you can't do it with Pythagoras. Does that make sense? But you can do it with trigonometry. So here's how you go about it. You say, well, let's look at one of these two angles. It's our choice, because this one's 30, so that means this one must be 60. As long as you know one, just pick one, okay? I've got this one drawn, so I'm going to focus on the 30. So looking at the 30, what ingredients do I have? I have the opposite, and I have the hypotenuse. Which one of your ratios has those two things in it?
Sine.
Have a look. Sine. So this triangle, if you say the sine of 30 degrees, and you write down what that's equal to using what you guys just figured out, it's opposite over
No, hypotenuse.
opposite over hypotenuse. That's how it works for this triangle, right? Then you've got a little equation, and you can solve it for x. It's a one-step equation. What you need to do to get x by itself, multiply by 74. If I'm going too slow for you, I'm sorry. I want to make sure everybody's on the same page. So that means x is 74 times the sine of 30 degrees. Wonderful! 74 times the sine of 30 degrees. That's the answer. I don't know how long that is. Do you guys?
No.
Yeah, no. But 30 degrees is from one of the special triangles. So if we go over here to the special triangle and take the sine of 30 degrees, we'll get a number. What's the sine of this triangle from 30 degrees? Let's do it. Opposite hypotenuse. That's 1/2. So this is 1/2. What's half of 74? Half of 70 is 35. And usually we're going to have units. Make sure if there's units, you get them. If this was like centimeters, make sure you call this centimeters. It's a length, right? We figured out that that guy is 37. Does it make sense? All you always want to think, does this make sense, kind of? Yeah, it could be 37. I mean, that makes sense. Yeah? Okay, so there you go.
Always going to be 1/2.
The sine of 30 degrees is always going to be 1/2. What if you're doing an equation and you're solving it and you come up with that you need the tangent of 45 degrees for whatever reason? Then you write down the 45, 45, 90 triangle from memory and you say, I'll pick one of these because there's two 45s. I'm going to go with this one. And tangent is opposite adjacent. So that would be 1 over 1, which is 1. What if you were solving an equation and you needed the cosine of 60 degrees? Because it's going to happen. And you say, write down this triangle. And see, the way to do this without having to stretch and actually try to memorize these is when you do the cosine of 60 degrees, should you go back in your notes, flip the page and look at this triangle? No! That's going to lead to problems when we do speed quizzes soon. This is going to be necessary knowledge. This is the most important thing in this unit, knowing these two triangles. No, you don't do that. You say, okay, I kind of remember what that 60-degree triangle looks like. I'm going to draw it again. Opposite 30, what was opposite 30? Oh yeah, 1. 60's over here, right? What's opposite 60? Oh yeah, root square root of 3. And the hypotenuse is 2 on that one. Okay, so cosine of 60, I'm going to go adjacent hypotenuse. That's how you do this. if you don't want to spend extra effort to memorize this. Now, of course, at the beginning, are you going to be able to do it as quickly as I did? No. But after you do about 3 or 4 problems, you're going to be able to do it as quick as that. And after you do about 8 or 10 problems, if you're doing it that way, it'll take 5 seconds to draw this triangle. Or you might not even need to draw this triangle. It'll be in your head so well. So that's the goal, okay? So you definitely want to do it that way. So if you're watching the video right now, I would recommend pausing and trying the second example problem. Why don't you guys try that? All right, so let's think about that second example on the worksheet. So it says find the value of x. What sides available do you have on that problem? Opposite and hypotenuse. Let's see, Dalton, that means which ratio should you use? The sine, great. You could also use actually the cosecant if you wanted to. That'd be more work though. So we'll just use the sine, okay? So what is the equation? Let's see, Ms. Ambler, can you tell me? Sine of 45 equals x over 20, okay, great. And that means you get an answer of x equals what?
20.
You end up getting 20 times the sine of 45, right? Which you guys already did. I heard some right answers. 20 and the sine of 45 from the triangle. Turns out to be 1 divided by the square root of 2. So this comes out to be 20 divided by the square root of 2. Now in trigonometry, it's not very common to see answers like that. You'll need to do something we learned in chapter 8, which was rationalize. Square roots don't belong on the bottom. That'd be a right answer. Like you put that on my test, you get the right answer. Does that make sense? But you're not going to see it that way sometimes, like in the back of the book and stuff. So to get rid of that square root of 2 on the bottom, you use a clever one. I'm sure most of you guys did not do yet because you don't have that reflex. But this is 20 root 2 over 2, which ends up being 10 root 2. That's a much better form of the answer. It's the one that would probably be in the back. Now, if you're on a quiz or test for me and you write that down, then that's the right answer and that's fine. But you might not recognize this if you don't know this little trick. Does that make sense? That happens sometimes on like the ACT, etc., lots of places. Now, of course, that doesn't really help you figure out how long this is. So you probably want to go to your calculator. So I'm going to go to my calculator and say 10 times the square root of 2. Square root of 2 is like 1.414. So that's 14.41, or 14.14. So that makes sense, I think, with that picture of that triangle we had, yeah? Okay, so let's look at something a little bit more practical that we could use this for. So here's a third problem. So it says we've got a park ranger. His eye level's 5 feet, and he's looking up at the top of a geyser erupting, and he measures the angle. I think he probably measures that angle with some kind of more precise device, but a nicer version of one of these. This is called an astrolabe. It's really easy to make one. I made one with a straw. Maybe we'll go measure those trees out in front and see how high they are one of these days. Because it's very impractical to go to try to measure those trees any other way. You don't want to get a cherry picker, like extend it all the way up to one of those tall pine trees and like get a giant measuring tape. That's like extremely expensive. Does that make sense? And for this guy, he doesn't want to go try to measure the geyser's elevation, how high it goes, because can you imagine the park ranger out there? Like with a big tall ladder out in the like boiling water? I think he's going to have some trouble. I'm just thinking he might die. I'm thinking that might happen. So he probably like measures the angle of elevation and uses a little trigonometry to figure out how high that geyser's going, okay? So on an application problem like this, the first step you want to do is draw an accurate picture. I'm going to spend a little time with the drawing, okay? So I'm not saying you have to be an artist, but like draw a picture, okay? So here's my park ranger. He is beautifully accurate, I know. Now where's the triangle going to be? The geyser's like somewhere over here, right? Like here's the geyser shooting out. And we said something about his eye level, so that's probably where I want to start my triangle. So I'll get my triangle going in here. But he's not looking there, right? Where are his eyes actually looking? He's got his astrolabe and he's looking up at the top of the geyser. We'll say it goes that high. And that's a right triangle, isn't it?
Yeah.
And now you want to attach the measurements that you know to that triangle. So what do we know about this triangle?
45 degrees.
What?
45 degrees.
45 degrees?
I mean 36 point.
So this is called the angle of elevation. So the angle of elevation is always measured up from a horizontal. You see these words in your assignment. Angle of elevation, you should always be thinking about a horizontal and going up from it. It's pretty hard to mess that up. Almost nobody ever messes that up. But there's also this other angle called the angle of depression. Everybody always messes that up unless they listen to me carefully. Because angle of depression also is referenced from a horizontal. That would be like if he was looking down into the ground. So if you've got like a balloon, I'm going to invent another scenario over here real quick. If you've got like an air balloon, and you've got a guy in this hot air balloon, and he's looking down at the ground over here. There's a couple different triangles in this situation which you'll be tempted to draw. Can you guys see that? Now there's two different triangles. So often people just draw this triangle because I don't know, it's just more natural to draw that triangle for some reason. And they'll put this as the angle of depression. It's a really easy mistake to make, but that's not the right answer. That's not the way it actually works. When he's looking down, he's depressing his eyes not by this much angle, but by what? Think about where his eyes are actually going. It's this horizontal, and from that horizontal, if you're looking up, that's the elevation angle. And if you're looking down, that is the depression angle. So be careful on your problems where you have depression angles. It's this one, not this one. Okay? Now, if you know this one, you can subtract from 90 to get that one and use this triangle if you want, or you can just go and draw this triangle and use that one. That's a judgment call. Okay? So maybe we'll look at one like that tomorrow. I think I'm going to try to have you guys figure it out yourself. That'd be better. As John Stuart Mill, we're reading about in philosophy, said, learning discovered yourself is always more powerful and long-lasting than stuff told to you by guys like this. Okay? So we need to figure out this geyser's height, though. So getting back to the geyser. Is there any other dimensions that I know?
Yes.
Let's do it.
Where?
With the range.
Like this number?
No, from the base, so that button.
Okay, this one?
Yeah.
All right. Anything else I know on this? Another measurement? I think we had one more.
You know, X.
We're trying to find this, right, over here. We could call this X, or I'm going to call it H for height. Okay? There's one other number I need to put somewhere. Noah?
You just said H plus 5.
Ah, good. Noah's saying H plus 5. I like that. I'm just going to say that let's remember he's 5 feet tall over here, and we're going to have to add that 5 at the end. That's good. All right, so we got a triangle. It's just like the one you guys just did, so let's do it. You can make it simpler if you want, redraw it. You don't need to, but there's H, there's 200. Okay, sides available. We have the opposite. We have the adjacent. That means we should use tangent. Tangent of that angle is opposite over adjacent. Solve that equation by multiplying by 200. Now sometimes your variable is going to be on the bottom. If your variable's on the bottom, what are you going to have to do? Multiply it up to the other side and then divide. It's not a hard equation if it's on the bottom. You've got to always multiply a thing up to the other side and then solve for the variable. Okay? So let's see, 200 tangent of 34.6 equals H. And see, this is a situation where we don't have a special triangle for 34.6. There's nobody who has that memorized except like, well, there probably are people, but not regular people who have that memorized. So we use a calculator to do that. In the old days, because this is math that goes back 2,000 years still, they'd have like a table of values, like a book, that they'd open up and say, oh, for 34.6, tangent's this. Then it would say 34.5, 34.3, and how did they figure those out to begin with? Involved a lot of pain in the butt work. Does that make sense? But nowadays we have a calculator. So let's go to our calculator and figure that out. Now, does that mean you could figure out the sine of 30 degrees on your assignment with your calculator? Sure. If you do it that way, you're going to be a hurting machine next week. So use the special right triangles when you can, and you'll be in good shape. Use your calculator on everything, you won't be in good shape. You'll be like those Hurt and Pueblo West calculus students that I talked to you about. So, So let's see, I think we just need to go 200 times the tangent of 34.6.
Where did you get your tangent? Oh,
There's a tangent button in the middle. Now, did anybody get a different answer than me? So I know there's going to be some different answers. Someone had to have a different answer than me. Everybody try it. Mr. Strickland?
I got 203.
You got 200 something?
Almost 33.
I like this. Is this 200 divided by the square root of 3, you think, Akash?
No,
No. Does this make sense for how high a geyser shoots, like Old Faithful? This is a big geyser, by the way.
doesn't.
I didn't tell you. I don't think that makes sense. That's a really short, weak geyser. It's a puny little guy. The park ranger probably doesn't care how high the puny little guy is. You know what I'm saying? So I think something's wrong here. The thing is, angles can be measured in lots of different units. They can be measured in things called radians, which we're going to look at Monday. They can be measured in things called minutes and seconds, which astronomers use. They can also be measured in degrees. You've got to tell your calculator how to measure. So on the top of your calculator, go to Mode, and there's something right away that says what type of angle is being measured in. We're using radians, whatever that is. We'll discover that Monday. I thought this problem was degrees, so you got to switch that. You always got to be careful about this. This is like the math student's bane if you're not aware of this. So make sure you're clear about what type of units your angles are being measured in. And then I'm just going to redo. I'm going to hit second entry, redo it. Okay, that makes more sense. This geyser's got to be higher than 8
At
feet.
times.
Right, so this was H. And then we've got to add 5 for how high the ranger was, because that's really this 5 right here. So we're going to get 142.971. That's about how high the geyser is. Make sure you get your units on there, and you're good to go. Okay, why don't you guys try that problem that's pretty similar, number 3, and we'll kind of leave it there today, I'm thinking. And number 4 tomorrow.